Okay, hi. Welcome back to indices. We're going to review the last bit that we learned last year about indices. This is having to do with fractional exponents when you raise something to a fraction. So we've done this last year, but it might be good for us to review a little bit again. Our aim is that we will be able to say after this lesson, yeah, I know how to use the laws of indices that have fractional exponents. All right, so starting off, first of all, here's what we're going to cover. We're going to cover, well, what about a unit fraction exponent, or when things work out simply, and then fractional exponents, which have a little more detail to them, and then looking at some problems that involve fractional exponents. Okay, so a unit fraction is just looking at something that's like a simple fraction. And if you had something like base 9 to the power half, base 9 to the power half, if you are multiplying, we know we add those exponents, right? So if we added them together, we would get 9 to the power 1, or just 9. And the same way would be true with 100 to the power half times itself. We'd get 100 to the power 1, but we don't write that usually. 49 to the power half times itself, we would get 49. So if we look at this, now knowing what we know about indices, look at this calculation. I have two things that are equal to each other that multiply to give 9. So I know what those two things are, right? Because I know what multiplies by itself to give 9. And so 9 to the power half must equal 3 because 3 times 3 equals 9. So if I have to have equal things that equal 9, they must be 3's. Or if you look at 100 to the power half, two things that multiply to give 100 that are equal to each other, it must be 10. So 100 to the power half must equal 10. Or 49 to the power half, what would that equal? What multiplied by itself gives us 49? Well, 7. So we can see by the laws of indices that we've already learned that raising something to an index or a power of half must mean that I take the square root of the final answer. So it must equal 9 to the power half must equal the root of 9, or the root of 100 here, or the root of 49. So the power to half means you take the square root of the base. Here's some for you to try. I'd like you to pause the video, write these down in your notebook, and come up with an answer, and then you can check your work. So pause the video and try these ones. Okay, welcome back. I hope you've got answers of 5, 6, 11, 7, 1, and 6. You can check your work there. So half must mean a square root. What about if we raise it to the power 1/3? Again, thinking about the laws of indices, if I had three numbers that were like 8 to the power 1/3, 8 times 8 to the power 1/3, 8 to the power 1/3, I have the same base, so I'd add the exponents. Well, if I add a third plus a third plus a third, I'm going to get 1, right? So 8 to the power 1, or 27 to the power 1 in the next case, or 1,000 to the power 1. So using that principle, I can again look at these calculations and say, well, raising something to the power 1/3, in order to make this correct, that must equal 2. Because 2 times 2 times 2 equals 8. So also, what must 27 to the power 1/3 be? Well, that must be 3, because this makes the calculation 3 times 3 times 3 equals 27. So the index of 1/3 must mean that I take the cubed root of that thing, because that's the number I need to have in order for it to make sense. by the laws of indices. So an exponent of 1/3 means the cube root of the base. Now, as we're thinking about fractional exponents, another way to understand it is to think of equations. Just another way of looking at it so that you can think, oh yeah, that totally makes sense. If I had two things that were unknown, but they have the same base, and I have something that is that same base and it's just on its own, then that must mean that I'm multiplying that thing twice. So in order to clear an equation like this, I know how I clear something if I have an equation where I have the square root on one side, or I mean the square on one side, giving it away, the square on one side, then I take the square root of both sides, and so that again makes it that a to any power here must equal the square root of a. You can also think of it like an equation. If I have 2m's equals 1, 2m equals 1, well then m must equal half. That's how it makes sense. So any base to the power 1/2 must be the square root of that base. So knowing that, we learned and we practiced last year that any fraction, you look at the denominator and you take the denominator's root of that base. So we would say a to the power 1/4 is the 4th root of a, and that's how you pronounce it. Or to the power 1/5, it's the 5th root of a, or to the 9th root of a, for the last one here. So again, look here at the screen and pause the video and just think, okay, can I match these? Do I know which ones match? And then what do these numbers in the center column equal? What is the final answer to this? Now you should be able to do these without using your calculator. I'll pause the video, you pause the video for a little bit, and then we'll see some answers. Okay, welcome back. So hopefully you're getting that this is a square root, cubed root, 4th root, and square root of 16. Now, what do these things equal? Cubed root of 64 is 4, square root of 64 is 8, square root of 16 is 4, and the 4th root of 16 is 2. 2 times 2 times 2 times 2 equals 16. So in summary, what we learned is that anything raised to a fraction, if it's 1 over something, then that's just that something root of the base. Now, what happens when we have an exponent, fractional exponent, where the numerator isn't just 1? So far, all we've talked about is like 1/2, 1/3, 1/4. So for example, if I have 16 to the power 3 over 2, what does that mean? Using the laws of indices, we know that I could break this down and I could put 16 to the power 1/2 in a bracket and raise it to the power 3 because I've learned I can multiply those, right? We talked about that last time. So if that's true, then I could take the square root of 16 and then just cube it. And sometimes, especially if it works out evenly, this is easier to do, just to use the unit fraction first and then raise it to the power. Here's the example. So if I take 16 to the power 1/2, square root of 16, cube that, so 4 cubed, which is equal to 64. So why don't you try this one? Rewrite it as a unit fraction, or think about it with me. You don't really have to pause it, but rewrite it using a unit fraction. It would be, I'll stick the numerator outside of a bracket. So 8 to the power 1/3 squared. Well, I know 8 to the power 1/3, that's 2. So 2 squared is 4. Or if I had something like 25 to the power 3 over 2, I could rewrite that as 25 to the 1/2 and then cube it. And I can quickly recognize, I know what 25 to the power 1/2 is. That's a square root of 25, which is 5. So then I have 5 cubed, which is 125. So whenever you have something, a base, raised to a fraction, you take it, the denominator's root, raised to the numerator's power. We'll look at that here. So the denominator root raised to the numerator's power. You can also, Izzy says, you can also write that as the bases raised to the numerator's power and then take the denominator's root. If it works out more quickly, sometimes that's easier to do. So is she correct? Yes, she's correct. Let's look at, so basically we're saying either you can have that numerator power inside the bracket or outside the bracket, either one. So you can find the root first, then you can apply the exponent, or you can apply the exponent and then find the root. And it just depends on what is simpler for you. So here's 2 student examples. So if you look on the left, Laura does it by doing the denominator first and then raising it to the numerator power. So she takes the 4th root of 81, which is 3, and then cubes it. Or if you want to, you can do the numerator power first, but then you get this great big number, and then you have to take the 4th root of that. It's possible if you have your calculator, but if you don't have your calculator, then you can see how Laura's method could be a lot simpler to work out. Here are some more questions. Now again, I'd like you to pause the video and to see if you can evaluate these ones and see if you can do it just as a challenge. See if you can do it without your calculator. So pause the video and then we'll correct them together. Okay, welcome back. So if you have the following answers, then you've got the right answers. A is 100, B is 64, C is 16, D was 27, E was 25, F was 16. Here's another little challenge. Thinking about a base 4, what exponent would I have to add, or an answer for, I shouldn't say a base 4, what exponent would I have to add to the 4 bases around it to make the number in the center? Or in case of 9, what exponent, what power would I have to add to the 4 bases around it to get the answer 9? Okay, so maybe jot this down in your notebook also. Pause the video and try it. And then let's correct it together. Okay, ready to correct it? Let's have a look. So if you were going to get an answer 4, then you have to raise these bases to these powers. And you can see that most of them are fractional, and that's because that's what we're practicing, but not all of them quite. So hopefully you got them. Let's look at a few problems with fractional indices, just to finish off here. Sometimes an answer doesn't always give you just a clear integer. And then you can either give your answer as a decimal, which your calculator might do, but sometimes it's better to leave your answer as a root. Apply all the laws of indices, and then whatever you have left in lowest form, leave as a root. Now this is where indices is coming into surds, and that's part of this chapter, chapter 3. But first of all, think, okay, if I had something 5 to the power 7 over 2. Well, the square root of 5 is not going to work out nicely, is it? But I could think, okay, how many 5s does this mean? And if I think about it as 5 to the power half, and I have that 7 times, I can expand that, or I can think about it expanded in my head. That means I've got 7 5 to the power halves. Well, 2 of these will equal 5 using the laws of indices. So here I have 5, and then I have 5, and there I have 5, and I have 1 left. So if I just take 5 times 5 times 5, which is 125, then I know I have 1 root 5 left. And I can write my final answer as 125 root 5. And that expression, or that term, is the exact value of 5 raised to the power 7 over 2. But much simpler to work with. As we go on, you'll see how much more simple it is to work with that. Try this one with me. If I had 2 raised to the power 9 over 2, if I wanted that as an exact value, well, the square root of 2 also doesn't work out evenly, does it? But if I have 2 of them, then I know that's equal to 2. So how many pairs can I get out of here? I've got 9 of these expanded, and here's 2, there's 2, there's 2, there's 2. Okay, so I've got 4 2's plus 1 2 to the power half left. So 2 times 2 times 2 times 2, that's 16. And then I have root 2. So 16 root 2 is the exact value of this expression, or this term. Now you try a couple. If I have 10 to the power 5 over 2, or 3 to the power 10 over 3, simplify those and write them as an exact value, not as a decimal. Okay, pause the video and try it. Okay, welcome back. Hopefully you got, by expanding it out or by thinking about it expanded, that I'd have 10 times 10 and then I'd be left with a root 10. So 100 root 10. And in the second case, I've got 3 to the power 1/3. And if I combine 3 of them together, I'll get a 3. So I have 1, 2, 3 whole 3's multiplied together plus 1 3 to the power 1/3. Which means I've got 27 cube root of 3 left in lowest terms. So to summarize, in this lesson we've reviewed how we can use fractional exponents and find what the answer is. If they work out evenly with the unit fraction, then you can just take the root of that number. But if the numerator is greater than 1, then we raise that to that numerator is the power that we raise it to, and we can express it in different ways. And that's all for this lesson. So you take care, and we'll see you again soon. Bye-bye.